Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics 3, RLT College of Science, Akola. Dear student, in previous lecture we have completed unit number 4. So from today we will start unit number 5, that is analytic continuation. So today we will see first topic of this unit number 5, that is direct analytic continuation. So before going to start direct analytic continuation, first we will see definition of the function element. What is the function element? The function element is defined as a pair of f and g. A function element is a pair f and g where f is a analytic on region g and g is a any region. F is a any function and f is a analytic function on region g. Okay. So here this is the pair of the function f and region g. So where g is a region and f is analytic on g. Okay. Second definition is a germ of a function. Let a pair of fg be a function element. It is called as a function element and a belongs to g. Then the collection of all the function element g comma d, function element gd, is called germ of the function f at a point A, and it is denoted by f suffix a. If and only f of z equals g of z for all z in same neighborhood of A. If function element gd belongs to f suffix a, or you can say that germ of A, then germ of A uh, then germ of a function f at A is given as function element gd such that a belongs to d, there exist r greater than 0 such that for every z belongs to neighborhood of a where f of z equal to g of z. Okay. Now we will see the direct analytic continuation definition. Let function element fd be a function element, then f2 d2 is said to be a analytic continuation of fd f1d and vice versa. If condition number 1, d1 intersection of d2 is not equal to empty phi, and second, f1 of z equal to f2 of z for every z belongs to d1 intersection d2. Okay, so this is the definition of the analytic continuation. Now we will see some problems on a direct analytic continuation. So first problem is show that f1 of z equal to summation n equal to 0 to infinity z to the power n, and f2 of z equal to summation n equal to 0 to infinity 1 plus z to the power n upon 2 to the power n plus 1 are analytic continuation of each other. So here we have to show that these two functions are analytic to each other, analytic continuation to each other. So we will see the proof of this problem. So what is given? So we have given f1 of z and f2 of z are the analytic function. Okay, and which are given as f1 of z equal to summation n equal to 0 to infinity z to the power n, which is analytic function for mod z less than 1. So therefore it is a convergent. So it is converges for mod z less than 1. Okay, so therefore the first function element f1 is summation n equal to 0 to infinity z to the power n mod z less than 1. Now second, f2 of z equals summation n equal to 0 to infinity 1 plus z to the power n upon 2 to the power n plus 1. So taking 1 by 2 is common, so summation n equal to 0, or this term can be written in this way. Okay, so therefore f2 of z is convergent for mod 1 plus z upon 2 less than 1. So we can write in this way, that is 1 plus z less than 2 to multiply here, dividing multiplying on both sides. So this can be written as z minus minus 1 of less than 2, that is z minus a. A is a minus a less than r. So here 2 is a radius and a is a circle. Okay. So therefore f2 of z is a function of f2 is summation n equal to 0 to infinity 1 plus z to the power n upon 2 to the power n plus 1 for the circle mod z minus minus 1 less than 2. Okay. So here f1 of z equal to summation n equal to 0 to infinity z to the power n equal to, we can write that is 1 upon 1 minus z for every z in mod z less than 1. Let us we consider equation number 1. Now second, f2 of z equal to 1 upon 2 summation n equal to 0 to infinity 1 plus z upon 2 to the power n. So this can be written as 1 by 2. So this can be written as that is 1 upon 1 minus 1 plus z upon 2 by using series formula, geometric series formula. Okay. So this is written as 2 2 will get cancelled, that is 1 upon 1 minus z, equation number 2. Here z plus 1 less than 1. So from equation number 1 and 2 we can say that f1 of z equal to f2 of z for all z belongs to d1 intersection d2. So therefore we can say that f2 d2 is an analytic continuation of f1 d, f1 d1. So in this way the proof of problem number 1 is proved. Now we will see second problem. Okay. So second problem is f1 of z equal to summation n equal to 0 to infinity z to the power n 2 to the power n plus 1, and f2 of z equal to summation n equal to 0 to infinity z minus I to the power n 2 minus I to the power n plus 1. Okay. So this example is similar to the example number 1. Okay. So if you try to solve this problem, so you can easily get the solution of this problem. Okay. Now we will see the next theorem. What is this next theorem? Let f1 of z be a analytic in domain D, and let f of z vanishes over a domain D0 which is a part of D. Then f of z vanishes at each point D. Okay. We will see the proof of this theorem. Let f be a analytic in a domain D, and let D0 be the any part of the region D such that f of z equal to 0 for every z belongs to D0. So to prove this theorem, let us we consider A be the any point in D such that A is not belongs to D0. Okay, and B belong to D0. Okay, here we will select a point A belongs to D such that A not belongs to D0 and B belongs to D0. And let L be the curve joining A and B and lying completely in B. It is possible because D is a connected region. So A let L be the curve joining A and B lying completely in B. Along this curve, we can find the point C such that along the CB equal to f of z equal to 0 and CA f of z not equal to 0. So taking limit z tends to C f of z, so we can say that this limit does not exist. So which implies that is limit z tends to C f of z is not equal to f of C. So which implies f is not continuous at a point C. Thus our assumption that f of z not equal to 0 along CA must be a wrong. So therefore we can say that f of z equal to 0 along CA. Since A is arbitrary, f of z equal to 0 for every z belongs to D0. Also f of z equal to 0 in D if it is 0 in region D0. Okay. What is the, we will see one example on this. Okay, so this is the second example which I have already given to you homework. Okay, so you can see the step by step example, so uh, you can solve with the help of this example. Okay, so you can see step by step how the example is solved. So this example is a similar way of example number 1. Okay, so you have to solve this example number. Okay, So dear student, uh, so today we have started unit number 5. So in next lecture we will see another theorem of this analytic continuation point.